This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 05. The ideal gas law and mixtures. Medium yield, 1 or 2 direct questions, but load-bearing for the Brayton cycle and any combustion product, compressed air, or HVAC problem where steam tables are overkill. Get the mole mass bookkeeping right and save 3 minutes per mixture question. Here's the problem. A rigid tank at 100 kilopascals and 300 Kelvin holds 3 kilograms of nitrogen and 5 kilograms of carbon dioxide, molar masses 28 and 44. Find the total volume, each species mole fraction and partial pressure, and the mixture gas constant. The mass-to-mole bookkeeping is where most students slip. The ideal gas law comes in 2 equivalent forms. Molar, PV equals N times the universal gas constant times T. Mass, PV equals M times the specific gas constant R times T. Identical, only the basis differs, moles or mass. R equals the universal gas constant over the molar mass M. Pick one basis per problem, molar for mixtures, mass for flow rate problems. When does the ideal gas model apply? Compressibility Z is PV over RT. Z equals 1 means ideal. Off 1 needs a real gas correction. 2 rules: temperature much greater than critical, pressure much less than critical. For air, that holds from 200 to 2000 Kelvin, below 5 megapascals. Essentially every exam problem with air. Water vapor is ideal only above about 300 Celsius at low pressure. In the dome, use the steam tables. Today's mixture at moderate P&T is comfortably ideal. Specific heat relations. An ideal gas has 2 independent specific heats. CV for internal energy change, CP for enthalpy change. 2 identities. CP minus CV equals R, and CP over CV is gamma. For diatomic gases like nitrogen, gamma is about 1.4. For triatomic ones like carbon dioxide, it drops to about 1.3. as extra vibrational modes absorb energy. For temperature swings over about 500 Kelvin, use variable CP from the gas tables. For modest changes, constant. Dalton's law of partial pressures. In an ideal gas mixture, each species acts as if alone at the total temperature and volume. Partial pressure equals mole fraction times total pressure. Partials sum to the total. Mole fractions sum to 1. The trap, mass fraction and mole fraction differ, equal only if all species share a molar mass, basically never. The exam gives masses, but asks for partial pressures, which need mole fractions. Always convert through moles. Build the variable table. 1 column per species plus a mixture column for totals, with rows for mass, molar mass, moles, mole and mass fractions, specific gas constant, and partial pressure. Givens are the masses, molar masses, total temperature, and pressure. Everything else is computed. Same T for all species. Verify both fraction sets sum to 1. A free sanity check. Pattern recognition. Air at low to moderate pressure and reasonable temperature. Ideal gas. Combustion products. Ideal gas mixture. A rigid tank, balloon, or piston cylinder at moderate pressure. Usually ideal gas. Percentages are usually mole fraction, but read carefully. Mass fraction or weight percent means convert to moles first. 2 red flags, an explicit Z off 1, or a state near saturation or supercritical. For steam, default to tables unless told to treat it as ideal. Handbook, quick reference. The ideal gas chapter covers the ideal gas law, mixtures, the compressibility Z factor, and equations of state like van der Waals and Redlich-Kwong. The universal gas constant and common molar masses are in the back matter tables. Worth memorizing: air 29, nitrogen 28, oxygen 32, carbon dioxide 44, water vapor 18. Solve. Step 1. Convert mass to moles, dividing each mass by its molar mass. Nitrogen comes out to about 0.107 kilomoles. Carbon dioxide about 0.114. Total about 0.221. Notice nitrogen is a minority by mass, but a larger share by moles, because it's lighter. Exactly why mass and mole fraction diverge. Step 2. Mole fractions and partial pressures. Mole fraction is each species moles over the total, about 0.485 and 0.515, summing to 1. Partial pressure is mole fraction times total pressure, about 48.5 and 51.5, summing to 100. Step 3. Total volume, two ways. Molar path. V equals total moles times the universal gas constant times T divided by P, about 5.5 cubic meters. Mass path. Get each species R as the universal constant divided by its molar mass. Mass weight them into R mix of about 0.23. Then V equals total mass times R mix times T divided by P, the same 5.5. Cross-check passes. For mixtures, the molar path is faster, since you skip R mix. Final answers. Total volume about 5.5 cubic meters. Mole fractions 0.485 and 0.515. Partial pressures sum to 100. R mix about 0.23. All cross-checks pass. Bonus, in the Amagat model, volumetric fraction equals mole fraction for ideal gases. Same number. Traps. 5 ways these problems lose points. 1. Mass fraction is not mole fraction. Dalton uses mole fraction, so convert masses to moles first. 2. Use absolute temperature, Kelvin, not Celsius. 3. Don't mix specific R and universal RU. Universal with moles, specific with mass. 4. Mayer Cp minus Cv equals R is per kilogram. The molar version uses the universal constant. 5. Ideal gas fails near saturation and the critical point. For steam in the dome, use tables. Near any critical state, check Z first. Quick recall summary. The ideal gas law in 2 forms. Molar with the universal constant. Mass with the specific constant. Mayer, Cp minus Cv equals R. Gamma is Cp over Cv. Dalton, partial pressure equals mole fraction times total pressure. Mass fraction differs, so convert through moles. Amagat, for ideal gases, volume fraction equals mole fraction. R mix is the mass-weighted sum of species Rs. Next up, Topic 6. The second law, entropy and isentropic efficiency. With the first law and ideal gas law in hand, we add entropy and the Clausius inequality. Then tackle isentropic efficiency for real turbines, pumps, and compressors, the trap that catches more exam takers than any other. Before that video for the same tank, compute each species-specific entropy from the gas table S0 values. PEPrepEngine.com/beta. The ideal gas mixtures cheat sheet, the worked problem PDF, and a 5-question quiz are attached. If the course helps you, subscribe.
The full study guide, with every equation and common exam trap, is free at PEPrepEngine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.